This is section 1.5, which is a continuation of identities. So let's get to it. All right, so for this first example, they want us to write tangent in terms of sine. So let's go ahead and do that. So we know that tangent is equal to sine over cosine. However, we're not allowed to leave our answer with the cosine on it because they're asking us specifically to leave it just in terms of sine. So if you guys recall, there's an identity, the Pythagorean identity, sine squared plus cosine squared equals 1. And then you can use this identity to solve for cosine. So if you solve for cosine, you will get cosine squared theta equals 1 minus sine squared theta. And then we take the square root of both sides, which introduces plus minus. So we get plus minus the square root of 1 minus sine squared. Perfect. And so that's going to pretty much do it. So our final answer will be sine, or plus or minus sine, over 1 minus sine squared theta. And the plus minus just depends on where theta what quadrant theta ends up being in. If it's in quadrant 1 or quadrant 3, then it would be plus. If theta is in quadrant 2 or 4, that means tangent would be negative in those two quadrants. So it just depends where that theta lies, which quadrant. All right, for this next problem, we're looking to expand this by multiplication. There's a couple ways you can do it. Some people like foiling. Some people prefer distributing this entire factor into this. I'll do it that way. I'll do the distributive method. So the first step would be to multiply the entire binomial by sine theta minus the entire binomial times 5. All right, there's your negative sign from here, or your subtraction. All right, and so now we can just distribute, and the subtraction also gets distributed. So this is going to be sine squared theta plus 2 sine theta minus 5 sine theta minus 10. 5 times 2, but the negative also gets distributed. So now we can combine like terms. That's going to leave us with sine squared theta minus 3 sine theta minus 10. And that does it. All right, next problem. They want us to simplify this expression as much as possible after substituting 3 tan theta for x. So we're using the substitution x equals 3 tangent theta. So if we plug that into this expression up above, that's going to be, well, we can also square this. X squared would be 9 tan squared theta. So actually we're going to substitute this because we have already squared it, so that makes it a little bit easier. So that's going to be 9 tangent squared theta plus 9. And as you can see, there's a common factor of 9, which we can factor out. So if we factor that out, you'll have tangent squared theta plus 1. And then the reciprocal of that, the square root of that, the 9 comes out as a 3. So now we have 3 square root of tangent squared theta plus 1. All right. And if you guys recall, this looks like an identity. That identity would be, let's derive it from the original identity being sine squared theta plus cosine squared theta equals 1. And if we divide everything by cosine squared, we end up with tangent squared plus 1 equals secant squared theta. All right, and therefore, now you can use this substitution which is equal to secant squared. So this expression becomes 3 square root of secant squared theta, which is going to be the absolute value of secant theta. Absolute value because you can't really take the square root of a negative number, so that's why we have to make that an absolute value. So that would do it right there. All right, as for the next problem, we need to prove this identity. So usually when you have an identity that you need to prove or verify, you always want to focus on one side and make that one side look like the other side. In this case, I'm going to make the left side look like the right side. So I'm going to start off by saying the left-hand side is equal to sine theta plus cosine theta to the second power, which means you write that twice. And now I'm going to work on this side and try to make it look like the right-hand side. This time I'm going to use the FOIL method. First, outer, inner, last, which would be sine squared theta plus sine theta cosine theta plus sine theta cosine theta plus cosine squared theta. If we combine the middle like terms, these two terms are like terms. That'll give us sine squared theta plus 2 sine theta cosine theta plus cosine squared theta. And automatically this should kind of turn on a light bulb in your heads. Sine squared plus cosine squared, hopefully you recognize that identity as being 1. So these two terms just become 1. And that's exactly what, so I turned this and this into 1 by the Pythagorean identity. And that's exactly what the right-hand side is. So that completes our proof. All right, so I like to start off by saying the left-hand side is equal to, and then I work on that side until I get it to look just like the right side. Then I say equal to the right-hand side, and that means we're done. And that pretty much concludes this section. So let's look at some homework problems now. I will leave these blank, filling in the blank problems for you guys. So these two are very similar. They're just different trig functions. So I will work on the first one, cotangent. So we know that cotangent by definition is equal to cosine over sine. All right, but they want us to write that in terms of sine theta only. So they don't want this. So as in the notes, same thing that we did in the notes, which is we used the Pythagorean identity and we solved for cosine. And we ended up getting the square root of, actually plus minus the square root of 1 minus sine squared theta. All right, and so that is what's going to replace this. And that will pretty much conclude that problem. Notice they already have the plus minus for you, so you don't need to write the plus minus. It's already there for us. So we just need to write the square root of 1 minus sine squared theta over sine theta. That would do it. All right, I'll skip this one because it's very similar to the problem we just did. Let's try this one. They say, write the following in terms of sine and cosine, then simplify if possible. Leave your answer in terms of sine theta and or cosine theta. All right, so we know tangent is equal to sine theta over cosine theta. And we also know that secant is 1 over cosine theta. So now we're just dividing two fractions, which means we're going to multiply by the reciprocal of the second one times cosine over 1. And then that will leave us with sine theta. All right, let's look at this one over here. Same thing. They want us to write this problem in terms of just sine and cosine and to simplify as much as possible. So let's write these out in terms of what their definitions are. So we know that tangent is sine over cosine, and we know that secant is 1 over cosine. Well, this is nice because we already have a common denominator. Sometimes you won't have a common denominator and you'll have to come up with your common denominator. In this case, it's already common. So we just end up with sine theta plus 1. And that's all we can do. And they say that to leave it in terms of those two values, trig functions, so that's good enough right there. Move on to the next problem. So these are very similar to what we were doing in the previous problem. So I think I'm going to leave that one up for you guys. So I will do this one. And that'll pretty much conclude this section. So let's look at number 7. So we do not have a common denominator in this case. So our common denominator will be cosine sine. So that's going to be cosine theta sine theta is our common denominator. So for this first fraction, we're missing a sine, so times sine theta times sine theta. For the second fraction, we're missing a cosine. So multiply top and bottom of that fraction by cosine theta. And now we have sine squared theta plus cosine squared theta, which hopefully you guys recognize as sine squared plus cosine squared. There's that light. Hopefully that light bulb is going off in your heads again. And that's 1. Pythagorean identity. And that will do it. 1 over cosine theta sine theta. All right. These last two problems are just multiplication problems, so you just want to expand this out using any method you like, FOIL or distributive or the box method. Same thing goes with that one. And I believe, there is a couple more problems left. All right, so let's look at this one. It says, show that the following statement is an identity by transforming the left side into the right. So we're going to focus on the left side here. And they pretty much guide you. They do a lot of the steps for us. So we got to just figure out what to put in the blanks. So it looks like secant has been converted already. Cotangent has also been converted. Cosecant has not. We know cosecant is 1 over sine, so that's exactly what we need to put in this box. All right, and now we are going to multiply by the reciprocal. So we got 1 over cosine theta times cosine theta over sine theta times the reciprocal of the denominator, which is sine theta over 1. All right, so a lot of simplifying happening here. Looks like we can simplify this and this, this and this. And the final outcome is just 1. Let's see here. What did they do? Sometimes it's harder to follow along their guided steps than it is to just do the entire problem by yourself. That's what I've learned with these. But it looks like you got the sine, cosine sine is here. And then this is going to go to the numerator. So that's going to be cosine sine as well. Because when you bring this up, you got cosine times sine over cosine times sine. So it's going to be cosine times sine. All right, and that's going to do it because as you can see, these are going to cancel. Everything cancels and leaves you with a 1. So that is the final step of that proof. All right, this one I will leave to you guys. Yeah, and once again, if you guys need any help on any of these, feel free to email me and I will be more than happy to help. We can do this one together. Let's see, so we got sine times secant plus cosecant. So we got sine times secant, which is 1 over cosine, plus 1 over sine, that's given to us. All right, and now we looks like we're distributing here. Sine over cosine, because when you distribute this, you multiply the numerator by sine, and you get sine over cosine. And then over here, when you distribute there, you get sine over sine, which is 1. And by definition,